The vector value function is a function that we input the real number in and we will get the real vector in n dimension. For example, this vector is the vector r, which is defined by t, and we will get the vector which is in n dimension. Each component will be the function of t. In 2 dimension, we will have the vector r, which is defined by t as well, and we will have component which is x position and y position. And this vector will point from the origin to the coordinate which is defined in this vector, and this one is called position vector. And when we change the value of t, the vector will change and trace along this curve. As well as in 3 dimension, we will have more dimension, and then the vector will be in 3 dimension. We will have the extra position which is z position, which is also the function of t as well, and then the graph will be like this, and then this one is position vector which is point to the coordinate x, y, z, and then when we change the t, the vector will trace along this curve t as well.
Now let's talk about the motion on a curve. So if you get the vector r, you can find the velocity by find the first time derivative and the acceleration from the second time derivative. And for the speed, you just find the magnitude of the velocity, then you will get the speed.
Since we know that the rate of change of r with respect to t is tangent to the curve, as you can see from the picture, and if we convert it into unit vector by divide it by its magnitude, we will get vector t. This vector t is called unit tangent vector, and here's the picture of how vector t lies on the curve. You can see that it is smaller than vector r because the size of it is 1. Here's our model. This model is about a particle moving along the helix path. The path is traced by vector r, but for the equation of vector r, we'll talk about it later. As you can see, there's 3 arrows. The pink arrow is tangent to the path, so the unit tangent vector is also in this direction. And you can see that when we move the particle along the path, the direction of pink arrow also change. So we can use this fact to introduce another parameter. This picture also shows how t change. So from this fact, as I said, we can introduce another parameter which is k. We call this k kappa curvature. And this k kappa defined by the rate of change of t with respect to s, and we put the size on the rate of change of t. Since we know from the previous section that the unit tangent vector t is defined by the lowercase t, so it's difficult to calculate kappa in this form. So we find a way to make it easier by using chain rule. We take dt by dt equals to dt by ds times ds by dt, and then we rearrange it into this form, and we can know that the denominator of this form is speed. So we can see that k equals to the magnitude of ds by dt, and then equals to the magnitude of dt by dt divided by ds by dt, and this equals to the rate of change of t divided by the speed.
The vector that we talk about is the normal vector. As you can see in this graph, its direction is perpendicular with tangent vector. So if we want to calculate the principal normal vector, so we use tangent vector and take derivative with respect to t.
In this model, that we use the green arrow as a normal vector, so we can see that if the particle moves along the path, the normal vector also perpendicular with the tangent vector and point to the center in every time.
After that, if you want to calculate the unit normal vector, so you use the normal vector and divide it by its side. And if we recall that k equal to the size of the tangent vector take the derivative with time t, time the speed. So the unit normal vector is equal to the tangent vector that take the derivative with time t divided by kv. That k is the curvature and v is the speed. Another vector that we talk about is located in 3 dimensions. That's perpendicular with tangent vector and normal vector. It's called B, the binormal vector. That we can calculate it by use tangent vector cos the normal vector.
So if we move the particle along the path, you can see the binomial vector direction always change.
From the picture, we can see that dB by ds is perpendicular to vectors t and b. Therefore, dB by ds must be parallel to n, and thus must be some multiple of vector n. This multiple is called torsion. Torsion measures the amount by which the curve twists. We can find the torsion by using the following formula. The minus sign is chosen to make the torsion of a right-handed helix positive.
From the model that you can see, we made the model of particle move along the path, and the path equation is equal to this vector r. We can find the velocity from the vector r is equal to the derivative of vector r. We are going to get velocity equal to this vector. We also can find the magnitude of the vector is equal to the square root of ijk square component square, and we got the magnitude of velocity. We can rewrite the velocity in the term of unit tangent vector. Unit tangent vector is equal to the derivative of vector r over the magnitude of derivative of vector r equal to this amount. We also need to find the derivative of unit tangent vector is equal to the derivative of unit tangent vector is equal to this amount. Next, we have to find the magnitude of the derivative of unit tangent vector equal to this component square root and take square equal to this amount. Next one, we are going to find the acceleration of the particle. The acceleration of the particle equal to derivative of velocity, and we use this equation, the equation of velocity, to take a derivative, and we got this amount, this vector. Acceleration can separate into 2 axes or 2 components. We can find a acceleration in the tangent component by using the derivative of vector r dot multiply with the double derivative of vector r over the magnitude of derivative of vector r is equal to this amount, and we got at is equal to 0, and another component is an. An is equal to the magnitude of vector r, derivative of vector r cross multiply with the double derivative of vector r over the magnitude of derivative of vector r, and we can find this part by the cross multiply in the determinant like this. We are going to get this vector, and we have to substitute this one into the equation, and we can find the an equal to this amount. It's a scalar vector. Is scalar.
We also can rewrite the acceleration in the term of n. N is unit normal vector. N can represent the direction of acceleration is equal to this vector. According to the 3 dimensions, we can find the unit binomial vector by using the unit tangent vector cross multiply with unit normal vector in the right hand rule. When we cross it together, we're going to get the b equal to this vector, and we can also find the derivative of unit binomial vector by take the derivative of this vector. We are going to get this vector.
This is the calculating of torsion and curvature. We can find torsion by minus the derivative of unit binomial vector dot multiply with unit normal vector over the magnitude of derivative of vector r is equal to this amount, the dot component. We can got the torsion equal to this amount. And we can find the curvature by the magnitude of derivative of unit tangent over the magnitude of derivative of vector r equal to this amount.